The term sustainable green buildings is generally used to define buildings that utilize high-performance components, properly designed and integrated, to yield desirable economical and environmental enhancement characteristics. A sustainable green building must incorporate the following critical features. These are efficiency in the use of energy and other resources, low life cycle cost, and a healthy environment for occupants. Success in achieving these valuable features is greatly influenced by the design and operation of the air conditioning system. The air conditioning system can have both enhancing and adverse effects. High-efficiency, high-SEER air conditioning units now available offer one way to enhance the energy efficiency of buildings. On the other hand, air conditioning systems often adversely affect building life cycle cost and internal environmental air quality as a result of water accumulation in unacceptable places inside the system, where it causes corrosion and damage to internal components and other surfaces, which shortens equipment life and allows and promotes the growth of mold, bacteria, and other health-threatening biological contaminants. In the air conditioning system, the only acceptable places for water are the cooling coil, condensate drain pan, and the drain system. All other places are unacceptable. To be effective, a drain system must overcome the pressures and airflow conditions created inside the drain pan compartment by the fan. Without an effective drain system, condensate flow is adversely affected. In draw-through systems, as illustrated here, water is blown back into the air handler, and drain pan overflow is common. In the industry, the most commonly used drain seal is the condensate trap, installed on the drain connection as illustrated. It uses water to form the drain seal. In theory, the design and operation is simple. The geometry of the trap is determined by the negative pressure created in the drain pan compartment by the fan. When the air conditioning system is not operating, the trap must retain enough water to effect a seal when operation begins. When the air conditioning unit starts, the trap water rises, negates the negative pressure, and prevents airflow into the drain pan. As condensate flows, the trap is filled, and the water column rises to a level necessary for condensate to flow from the trap. When the unit cycles off, the water returns to the trap and the cycle can be repeated. In theory, the condensate trap appears to be a simple and economical drain seal. In practice, however, it exhibits so many failure modes that it imposes unacceptable damage and contamination on the entire air conditioning system and the building. Many of these critical failure modes were identified by ASHRAE in their standard 6289R, which discusses drains and drain pans in paragraph 564. What ASHRAE standard 6289R says about condensate traps is quoted as follows. Condensate traps exhibit many failure modes that can impact on indoor air quality. Trap failures due to freeze-up, drying out, breakage, blockage, and/or improper installation can compromise the seal against air ingestion through the condensate drain line. Traps with insufficient height between inlet and outlet on draw-through systems can cause the drain to back up when the fan is on, possibly causing drain pan overflow or water droplet carryover into the duct system. The resulting moist surfaces can become sources of biological contamination. Seasonal variations such as very dry or cold weather may adversely affect trap operation and condensate removal. The trap failure modes identified by ASHRAE can be divided into three categories: those due to inherent trap deficiencies, trap design deficiencies, and unwise field practices. Inherent trap deficiencies include unavoidable and frequent flow blockage, susceptibility to freeze damage, dry and useless at startup and wintertime, and dry and useless on secondary drains. These deficiencies are common to any trap, regardless of the design. Design deficiencies of traps include improper trap depth, incorrect height between trap inlet and outlet, no provisions for priming and cleanout, specifying traps for secondary drains, trap or drain seal not specified, or the inadequate space for installing a trap or drain seal. Unwise field practices include double trap airlock, trap removed, failure to clean trap regularly, failure to prime at startup and wintertime, and leaving the port for cleanout and priming open. The damaging and health-threatening conditions caused by trap failures are widespread. In this country, millions of systems are equipped with condensate traps, a situation which virtually ensures that some buildings will never attain a true sustainable green building status. The seriousness of trap failures and their effect on sustainable green buildings is not fully appreciated by many in the industry. This lack of appreciation is understandable. Air handlers and other components in air conditioning systems are enclosed, and internal damage is not readily visible to the owner or service personnel. Typically, what they see during operations are units like those shown in the top photographs. Only when the cabinet is open can the damage be revealed, as shown in the lower photographs. But even then, the causes are not apparent. But they can be illustrated vividly using laboratory simulated air handlers with transparent panels. These simulators allow building owners and other concerned parties to see and understand how trap failures cause damage and contamination to their air handlers and buildings. To illustrate the problems caused when a system is operated without a trap, the laboratory simulator is being operated with a negative pressure near 1/2 inch of water, typical of small draw-through systems. Deflection of the benzene lighter flame shows how contaminated air can be drawn into the unit, and the introduction of smoke near the drain outlet shows how polluted air can be drawn into the system and spread into the conditioned space. The two views, one inset, show the blowing of condensate as the drain pan fills, and that it continues even after condensate begins to flow from the pan. Even greater problems arise when systems are operated at a more negative pressure. Here, operation is at a negative 1.5 inches of water. Systems are often operated at this or more negative pressures. As can be seen, condensate blowing becomes intense. Flow cannot occur at this pressure because water will overflow from the drain pan before drainage can begin. Also, as shown by blue paper placed in the blower discharge stream, water particles can be carried into the ductwork and cause damage to insulation and other components. Here, the effect of operating a system with an empty trap is illustrated. During startup for summer cooling, the empty trap acts like a missing trap, causing similar damage and contamination to the system and building. Debris and algae growth frequently block traps as shown here and cause drain pan overflow. This is one of the most common causes of building property damage and contamination. Condensate traps exposed to freezing temperatures are frequently ruptured, as depicted here. Since a ruptured trap cannot retain condensate, it acts like an empty trap. Observe that water leaks from the trap and allows air ingestion and condensate blowing during the cooling operation. Ports provided for trap cleanout and priming must be covered during all operating conditions. If for maintenance conveniences the port is left uncovered by design or service personnel, the trap acts like a missing trap and causes all the same problems. The effect of operating an actual draw-through system without a trap is shown here. Note the condensate spillage from around the edges of this particular unit. Now, using a transparent panel to observe further, see that condensate has overflowed from the drain pan and that the blowing is much like that shown by the simulated air handler. The consequences of trap failures, including those just demonstrated with laboratory simulators, are summarized here. High-velocity air entering through failed traps can blow condensate into the system and ductwork. In addition, high negative pressure or flow blockage can cause the drain pan to overflow. These events cause damage to the air handler and the building, creating a perpetual internal wetness, a fertile growth place for mold, bacteria, and other health-threatening biological contaminants. The property damage and maintenance effort required for this type system eliminates any hope for low life cycle cost. Further, since all the air inside a building may pass through the contaminated air handler several times per hour, health-threatening conditions are virtually certain. Thus, the use of systems equipped with condensate traps in reality rules out the realization of sustainable green buildings. The photographs that follow show examples of the damage that condensate trap failures cause to equipment and buildings. These photographs show a small rooftop air conditioning system, which was operated without a trap as a result of an inherent trap deficiency and an unwise field practice. The damage and contamination shown are the results of flooding caused by a blocked trap, and were accelerated by condensate blowing and possible flooding when the trap was removed. This large indoor air handler has two traps, primary and secondary, that exhibit both inherent and design deficiencies. Observe the damage and contamination caused by these traps. Note, the design includes no provision for priming. Unprimed during winter operation, outside air is ingested through both traps. At startup for summer cooling, the primary trap allows condensate to be blown from the pan and possibly cause overflow. Whenever overflow occurs and reaches the unprimed secondary drain trap, the same condensate blowing and overflow conditions are repeated. The resulting system damage and contamination are inevitable. Far too often, HVAC systems fail to successfully dispose of the condensate they generate. It then ends up on internal surfaces of the air handler as shown in these photographs, or on building components as pictured here. The wetted surfaces cause corrosion and provide a fertile growth place for contaminating organisms. Commonplace and widespread, the results are costly property damage and significant health threats. The trap drain systems shown here meet both uniform and international codes, which simply state that drain systems must be trapped. The geometry of the traps vary greatly, but they represent the industry standard design. These traps, and the conditions that often accompany them, are clearly unacceptable. Therefore, a reliable condensate drain system is required.
A practical solution to these problems is the CostGard Condensate Drain Seal, a seal designed, developed, tested, and patented by a professional engineer with expertise and many years of experience in the dynamics of fluid flow. It has been proven in both the laboratory and the field. The seal protects the building owner or user against undue cost in terms of maintenance effort, property damage, early equipment replacement, and health care. For this reason, the word CostGard is used to identify this seal. The seal is simple, has no moving parts, and is self-regulating. How the CostGard Condensate Drain Seal functions can easily be explained by use of a simulated air handler. A small quantity of air is taken from the positive pressure side of the blower. A portion of this air is discharged through the condensate drain pipe to ensure that outside air and pollutants are not drawn into the system. The remainder of the air is directed through the mitered elbows into the air conditioning unit. The air pressure loss in these elbows ensures that the air velocity entering the condensate drain pan is too low to cause condensate blowing. At the same time, the seal allows condensate to flow freely from the drain pan. CostGard condensate drain seals will operate successfully with internal negative pressures of 5 inches of water. The CostGard device being demonstrated here is operating at a negative pressure of 1.5 inches of water, typical of air conditioning systems of up to 30 tons. Note that the benzene lighter flame is being blown away. Thus air and pollutants cannot enter through the drain connection. Note the two views. In the inset, observe there is no blowing of condensate. Note also that flow discharge is smooth. With the aid of a transparent panel, the effectiveness of the CostGard condensate drain seal in preventing the blowing of condensate in a real system is shown here. Notice that condensate blowing stops as soon as the seal is in place and that condensate begins to flow. Now, with the transparent panel dry and the CostGard condensate drain seal installed, note that there is no condensate blowing and that condensate flows smoothly from the device. A typical field installation of the CostGard condensate drain seal is shown here. By means of a transparent panel, you can see that no condensate blowing is taking place. This unit was wet inside and covered with mold before the CostGard condensate drain seal was installed 3 years prior. Now it is dry and there is no visible mold. One of the biggest problems with a condensate trap is that it catches debris and becomes blocked. This happens frequently, often after only 6 months of operation. The CostGard condensate drain seal inherently guards against such blockage. This special CostGard device, equipped with clear plastic elbows, shows why. Here soggy oatmeal is used to simulate the slime that often clogs drain lines and traps. Note the churning action produced by the air entering the device and the rapid passage of the debris. Unlike the condensate trap, the CostGard condensate drain seal retains no condensate. Once condensate flow ceases, the warmer air that forms the drain seal quickly evaporates any water that may be held in place by surface tension.
A key feature of the CostGard condensate drain seal is that it uses an air seal in place of a water seal, and therefore prevents the problems caused by condensate traps. It eliminates the ingestion of noxious and toxic gases through the condensate drain line, the blowing of condensate by air entering the drain connection, flooding caused by excessive negative pressure or trap blockage, and it precludes the possibility of seal destruction by freezing temperature. It is simple, has no moving parts, is self-cleaning, self-regulating, and virtually maintenance-free. And it costs less than a typical service call to clean a trap, not including the damage caused by the trap failure. These features of the CostGard condensate drain seal offer building owners numerous benefits. Reduced life cycle cost by decreasing maintenance effort, equipment corrosion and damage to the building and contents, and improved environmental conditions by limiting system internal wetness that promotes the growth of health-threatening biological contaminants, therefore making sustainable green buildings possible.
By converting new units from this condition to this condition, and by converting older units from this condition to this condition, thus offering the building owner significant cost reduction plus improved indoor air quality.
The CostGard condensate drain seal is applicable to any draw-through air conditioner, unitary or split, with cooling capacities up to 100 tons, drain sizes 3/4 inch to 2 inches in diameter, drain pan pressures to a -5 inches of water, both indoor and outdoor locations, all kinds of climates, hot and humid to cold and dry. 4 typical field installations of the CostGard condensate drain system are shown here. Note that in order to form the air seal, 3 pipe connections are required. In addition to the drain pan connection, 2 other pipe connections are necessary. One pipe enters the drain pan compartment at point A. The other pipe enters the air supply plenum or air supply duct at point B. The CostGard condensate drain seal system has been operating successfully in various applications for more than 20 years. These systems are exposed to a wide range of geographical and environmental conditions, extending from Puerto Rico to Alaska, from Maine to Hawaii, and every state in the United States, including the District of Columbia. Some current users of CostGard condensate drain seal systems are listed here and include commercial and public buildings, schools and universities, and medical facilities. The commonality among these building owners is that they have competent technical support and/or well-qualified maintenance personnel, each committed to achieving buildings with low life cycle cost and healthy indoor environments. Users' comments on the performance of the CostGard condensate drain seal are typified by an internal e-letter from a Walgreens maintenance person. It reads, "In the years we've been getting the RTUs with the Trent CostGard drains on them, the evaporators are the cleanest we have ever seen them. Nothing like the old-style trap that just clogged up in summer and froze in wintertime, and that has helped to eliminate calls regarding water flowing back into the stores. They truly are paying for themselves." Walgreens now has more than 8,000 stores equipped with over 32,000 CostGard condensate drain systems, a significant step towards sustainable green buildings. CostGard condensate drain seals are available in 3 different kits: a basic kit, custom kit, and a system kit. Basic kits include all non-standard components needed for installation and are suitable for all manufacturers' rooftop units and split system air handlers up to 30 tons, with drain pan pressures to -1 1/2 inches of water column, and are available in 3/4 inch and 1 inch drain sizes. Custom kits include all non-standard components needed for installation and are suitable for all manufacturers' rooftop units and split system air handlers above 30 tons, with drain pan pressures to a -5 inches of water column, and are available in 3/4, 1, 1 1/4, 1 1/2, and 2 inch drain sizes. System kits include all components for installation and are available for over 500 Carrier, Train, Lennox, and York rooftop models up to 30 tons, with drain pan pressures to a -1 1/2 inches of water column, and are available in 3/4 inch, 1 inch, and 1 1/2 inch drain sizes. All CostGard condensate drain seal kits are available directly from Trent Technologies. System kits for unitary rooftop units are available from 3 major equipment manufacturers who make provisions for easy installation and/or ship the appropriate kit with their equipment. York Source 1 offers basic and system kits to York distributors. In summary, the CostGard condensate drain seal is widely used, effective, reliable, and a practical means for draining condensate from draw-through air conditioning systems. Sustainable green buildings are not possible unless equipped with properly drained air handlers. Building owners can ensure their green buildings are not unnecessarily compromised by air handlers by simply instructing designers and/or builders to equip all draw-through air conditioning systems with CostGard condensate drain seals or the equivalent. A reliable equivalent to CostGard condensate drain seals can be stated in terms of performance as follows. The drain seal shall, under all operating conditions, allow condensate to flow freely from the pan, prevent outside air from being drawn into the units, and eliminate the blowing of condensate from the pan onto internal components. Avoid condensate overflow caused by flow blockage or negative pan pressure, not be affected by algae growth, not require priming at any time, preclude damage caused by freezing temperatures, have no moving parts, be self-cleaning and self-regulating. An inside view of air handlers that use the current industry standard versus the CostGard device are quite revealing. These photographs show the damage and contamination caused by trap drain systems after less than 10 years of operation. And these photographs show units using CostGard drain systems after more than 13 years of operation with no preventive maintenance. To assist specifying architects and engineers, Trent Technologies provides a CSI format specification and AutoCAD drawings for CostGard drain systems. These files are available for download from our website, trenttech.com.